My name is Jeff Metley. I'm with HBM nCode, and today we're going to look at applications for Powertrain and look at factor safety analysis. When looking at Powertrain components, there's a wide range of components involved with the Powertrain, and each one has differing methodologies required for the durability assessment. There's components such as crankshafts, camshafts, pistons that may be analyzed with factor of safety alone. There are components mounted to the engine, bracketry, components such as fuel rails that many times are signed off with random loading tests. There are components such as the transmission gearbox that may require both high or low cycle fatigue calculations. And finally, there's components such as the turbocharger exhaust, which will require temperature compensation to accurately characterize their fatigue performance. Today we're going to look at certain capabilities inside of DesignLife to enable those styles of calculations. We'll look at factors of safety, both stress-based and life-based, and actually mention today that the stress-based are new in 9.1. Everything else today is going to be current 9.0 or before. We'll look at fatigue calculations in the frequency domain in terms of virtual shaker table. We'll look at the automatic compensation for notch sensitivity that's available for FE-based analyses in DesignLife, and finish up looking at temperature corrections in terms of isothermal and thermo-mechanical fatigue. The nCode product range, actually currently today, is 3 products. There's GlyphWorks, which is a tool that looks at measured data and allows you to graphically and interactively analyze, characterize it. There's Automation, which is a web-based data management tool that manages, again, measured data. And finally, today, our focus is going to be on DesignLife, which utilizes FE results to do upfront fatigue predictions. Well, what I want to do is start out looking at factors of safety, and actually the stress-based factor of safety capability is new in our 9.1. And it literally is nothing more than looking at some target stress magnitude divided by an operational stress or a cycle stress magnitude. The target stress can be obtained, well actually is obtained on a constant life curve. And this constant life curve can be defined in 2 different ways. One, we can import it directly as a Hague diagram. And Hague diagram is an SN material format that is just standard inside of the nCode Material Manager. It can be brought in either directly as an exact curve, or it could be brought in as a family of curves and interpolated between them. And the curves themselves can be automatically compensated for things such as surface treatment and certain survival. What you're looking at here is an example of Hague constant life curves that are inside the nCode material database. Each one of these curves, actually, if you look at the graph first, the horizontal axis represents the mean stress of a cycle. The vertical axis is basically representing the stress amplitude, the size of the cycle. Each one of those curves represents a constant life, a set of mean stress and amplitude that along the curve give you exactly the same life. And in this particular material, we have 6 curves at 6 different lives. Again, we could use a single curve in the factor safety calculation directly, or we could bring in a family of curves and interpolate between them. The other approach to generating this constant life curve is to start with a standard SN fatigue definition, and with that and a target life, we can generate a target stress at a zero mean stress, and then use an empirical mean stress correction, such as Goodman or Gerber, to construct the constant life diagram. And again, the initial fatigue curve, SN fatigue curve, could be pre-treated, compensated with things such as surface finish or certainty survival prior to the calculation. So we start with an SN curve out of the database. Again, we would apply things like surface treatment corrections, certainty survival to it to generate the curve we're going to use for the fatigue analysis. And then as part of the input to the factor of safety, you specify a target life. This is the life you want to achieve or compare your performance to. And that's used to go in, look at the corrected curve and calculate a stress target for a mean stress of 0, and our ratio of -1. That stress target is then used to construct a constant life diagram. And what we're looking at here is, again, a constant life diagram where the horizontal axis is mean stress, vertical axis is stress amplitude. The point we've just calculated, that target stress, is a location on the vertical axis. It's the stress amplitude of our target life with no mean stress. And then these curves represent empirical basically empirical constant life diagrams. And you have the option of using Goodman or Gerber with or without compression corrections, as well as an FKM mean stress correction. Once I have this constant life diagram, I now have the ability to go off and to calculate my factor of safety. To do that, we look at the actual stress cycles that are in our time history. And again, those stress cycles can be created from a variety of different loading types, load providers inside of DesignLife: constant, time series, time step, duty cycle. Stresses coming out of those load providers can be corrected for notch sensitivity, which we'll talk about later. And then they are rainflow counted to basically identify cycles. And we take these cycles and break them into amplitude and mean. That stress cycle is compared to our constant life diagram and used to calculate a factor of safety. And in the stress-based factor of safety, we report the factor of safety for the worst case cycle with the lowest factor of safety. You can see there's actually two forms of this factor of safety that can actually be computed. One is constant R ratio, the other is constant mean. Take a look at the diagram. Again, go back to the constant life diagram. This is a constant life diagram that's using a Goodman correction that has a correction only in the tension region. The compressive region is left alone. And the red dot you see is actually the stress state for one of our cycles. So what we have plotted here is the stress amplitude, which is the vertical, and stress mean, which is the horizontal, of that stress cycle. We're going to compute the factor of safety initially here as a constant R ratio factor of safety. This is a factor of safety that assumes that the mean stress is basically created by the operational load. So as I increase the load, the mean stress increases. To actually get the factor of safety, we calculate a vector that goes from the origin through our stress point up to the constant life diagram. And then we calculate the distances from the origin to the stress point and the origin to the intersection of the constant life diagram. And the ratio of those, basically the ratio of the distance to the constant life diagram divided by the rate, the distance to the stress point, is our factor of safety. Again, a factor of safety greater than 1 means that we have a design that passes our stress target. Less than 1 would be missing the target. There's a second way to calculate this factor of safety, and that is looking at a constant mean stress. This would be a condition where the mean stress is created by something other than the loads, possibly an assembly condition, something leaving a residual stress where the mean stress is pretty much independent of the loads applied. Here we look at the intersection with the constant life curve as a vertical line, again leaving a constant mean stress. And as before, we're looking at the ratio of distances, distance from basically a zero amplitude, or that horizontal line, up to our stress state, and then again up to the intersection with the constant life diagram. And the ratio of those distances gives us the factor of safety. I'm going to go in and bring up the software quickly. Okay. I'm going to start DesignLife. DesignLife, if you haven't seen it, is a process-oriented durability solution using finite elements. And the first thing I'm going to do is open a pre-existing process. It's one I had created earlier today. In this process, I actually have the FE model already insert. And what this is the one throw of a crankshaft where I have two loads applied to the throw, one being a horizontal force. A second separate force, a separate load case, is a vertical force. I've taken and paired those forces up with two load histories, one being a sine wave, one being a cosine wave. The goal here is to represent a load that basically rotates 360 degrees. If I look at the factor of safety glyph, the glyph being this solver, I have two sets of inputs. One is a definition of an SN curve. Here I'm going to point to a fatigue curve and use that fatigue curve to discern my target stress and hence create my constant life diagram. And if I were to look at that fatigue curve in the database, what I have here is an SN curve that represents the stress range versus number of cycles. The other inputs that I have here are properties that are controlling the factor of safety calculation. So I have here properties that discern how I take the stress tensor and turn it into a scalar for rainflow counting. I'm doing a critical plane analysis. I have controls that specify whether I'm doing constant mean or constant R ratio calculations. I have controls that specify the mean stress correction I'm using. And I have a target life here. This target life was used along with the SN curve to create that target stress for zero mean stress. Since I've run the application up to the solver, you'll see that I also have exposed the two load histories that are coming in and pairing up with my load cases, my sine load and my cosine load. Once I have these all set, all we need to do is hit the run button, and we actually execute the program. Here, every node in the model is going to calculate a stress history. That stress history is going to be cycle by cycle counted, mean stress, and basically compared to our constant life diagram, which is doing the mean stress correction on a target stress that we've defined. Results for this, again, are just a model-wide factor of safety. And again, this factor of safety represents the actual operational stress cycle against the target stress that we've calculated with the SN curve and our target life. Coming back to the presentation, we're going to look at a second style of factor safety that's been DesignLife actually for many releases. Though at version 9 there was some enhancements to give more user control to the minimum and maximum limit that was allowed. This factor of safety is actually calculated as a scale factor I apply to my loading condition to obtain a target damage. So I'm actually doing a fatigue calculation here, and I specify a given target damage that I want to hit, and it will calculate for every node in the model a scale factor for the applied loads that would give me that target damage. It uses a facility inside the solvers that's called back calculation. And so back calculation, typically when we do a fatigue analysis, we bring in a loading, we specify a material, and a forward calculation would tell me the life at every node. The back calc goes in, is specified a damage and hence a life, and it goes in and iterates on the loading to come up with a scale factor that would basically give me that life. It's available in both high cycle and low cycle fatigue, stress life, strain life. It's also available in spot weld and seam weld. It can use any of the time-based load providers, constant, time series, time step. It allows for notch sensitivity corrections to be done both for stress life and strain life, and also allows that things such as surface finish corrections as well as certainty survival could be applied to it prior to the calculation. And kind of graphically looking at what it's doing, what I have here is a forward fatigue calculation where we have a fixed time history going through rain flow counting. Each cycle is compared to the fatigue curve to get damage. Individual damages are summed up to give a final life. In terms of back calc, what we do is we start out by specifying a target damage. This is the value we want to be calculated at every one of our nodes. And then what we do is we take the time history in the upper left-hand corner and we iterate on it until we find a scale factor for that time history that would give me that target life for that particular node. That scale factor, in essence, is the factor of safety that we present. And if the time history I was bringing in was a single cycle, this scale factor would be identical to a constant R ratio factor of safety. One difference between the stress-based and life-based calculations, the stress-based is giving you a factor of safety solely on the worst cycle. The life-based is giving you a factor of safety on the entire damage, the damage created by the entire time history. Okay, we're going to move on and look at fatigue caused by random vibration. We can liken this to a virtual electro-dynamic shaker table. If we look at components, many of them on the engine mounted with brackets or things like fuel rails, many times we have to qualify those with a random loading, and we do that on a test rig that is an electro-dynamic shaker table. To do this, we program in a random signal. It may be acceleration, force, into our shaker table, and what will happen is it will generate a random loading representing that PSD, let's say, of acceleration, and apply it to our part. And the qualification test will be so many minutes, hours, days of excitation with this random loading. We can use DesignLife to do that virtually. So exactly the same simulation that we saw on electrodynamic shaker table, but using DesignLife as a virtual shaker table. And to do that, we bring in the results from a final analysis that's basically steady-state dynamics or harmonic analysis. This would be a unit excitation sweep of some acceleration, force, displacement on our part, And what we get out now is, for every node in the model, the transfer function of, if I put in a input at this excitation location, what would be the output of the node that I'm looking at. In addition, we pair that with exactly the same PSD excitation that we would have put into the physical shaker table. And then finally, DesignLife will take those two and compute a PSD of stress for each node in the model. And that PSD of stress can be cycle counted. There's 4 different cycle counters inside of DesignLife to look at PSDs of stress and generate stress cycles. And once I have stress cycles, I can use that along with a material fatigue curve to calculate individual cycle damages and hence total damage on the part in terms of minutes or hours of operation. So the result now is a contour map of life in terms of time it takes the part to fail. Looking at this in a real case, I have a DesignLife process here. On the left-hand side are 2 inputs. The upper input is the FE results from this steady-state dynamics analysis. And again, that's kind of the transfer function. The lower input on the left-hand side is a PSD of excitation. You can actually see the PSD that's been brought in on the adjacent XY display. Again, these 2 inputs are used by vibration fatigue to go in and calculate a PSD of stress at each location in the model. And once we have a PSD of stress, there are cycle counters built into DesignLife that can count the number and size of cycles, and with that I can predict fatigue. Looking at this example, it was actually run in DesignLife as a virtual vibration test, predicting an overall life of 600,000 seconds. On the proving ground, the part failed in 140 hours, or about 500,000 seconds. So we're looking at a fatigue prediction there of around 20%. Again, this can be very, very important, allowing us to go off and, prior to creating parts, be able to go off and to certify the part in the physical qualification test it needs to see once it's been created, or on the proving ground as well. I'm going to move on and look at another capability inside DesignLife, and this is the ability to account for notch sensitivity. When we run an FE analysis, we get stresses out that represent fundamentally the exact stresses from the stress concentrations, the notches in our FE model. And fundamentally, those stress levels are solely dependent on geometry and loading. They're really independent of material. So whether I had steel, aluminum, or polymer, I would have virtually the same stress there. The issue is, with certain materials, the levels of stress that we see, these elastic stress concentrations, don't match their performance in fatigue. This is especially true of metals that are cast. Things like gray cast iron you find, or ductile iron you find in a powertrain application in terms of block or crank, tend to be quite notch insensitive. What we mean by that is, in this particular display here, I have a fatigue test of a smooth shaft, and it gives me the fatigue behavior of that pure material with no stress risers. If I were to take that material definition, that fatigue definition, go up and do a finite element analysis of a part with the stress riser in it, get the stresses out of my finite element analysis, and use the material properties that I calculated from the unnotched specimen, I would predict a fatigue performance you see as this lower curve down on my plot, the one that says KT of 3.1. However, if I were to take that part create that part with the notch, and do a fatigue test on it, I may not get that poor performance. In fact, in this case here, you'll see the second curve up, it actually gives you a much higher fatigue performance. A performance that here it's saying is a notch factor of 2.2. The key here is the material that this part was made of is not completely notch sensitive, and so that stress at the notch isn't fully effective in fatigue. Another way to look at this is if I have, again, a fatigue curve of pure material, an unnotched specimen, and I then go in, take my notched specimen and test it, I will see I have a degraded performance. I have a fatigue curve that's lower. But that reduction isn't necessarily always the same as the stress concentration factor I get on my final program. That reduction factor for the fatigue curve we call KF, or fatigue notch factor. The stress concentration factor we see we call KT, or it's elastic stress concentration factor. And for certain materials, again, for a lot of cast materials, this notch factor may be significantly lower than the stress concentration factor. The way we can account for that inside of DesignLife, there is the ability in DesignLife when we get the stresses for the part that we can also calculate the stress gradients. On the left-hand side, you see kind of a schematic where we have a notch in a part, and at the bottom of the notch, we're obtaining the stress from the final element results. We also have the ability to drill into the part and to calculate how quickly that stress drops off, or the stress gradient. That stress gradient is used to estimate the sharpness of the notch. And with that information and material information, and again, we've built the material information into DesignLife, it was obtained from a fatigue design guide, the FKM design guide out of Germany. And these curves on the right-hand side represent the fatigue performance of different grades of steel, or actually grades of materials here. We have steel, and cast irons at different UTS values. And this material definition allows us to go in and look at what the stress gradient is along with the style of alloy and its strength and calculate a correction factor. And you'll see the correction factor in the middle of the page. This correction factor is literally nothing more than the elastic stress concentration factor divided by the notch factor. The beauty of this parameter is, if you remember, what we get out of a final element analysis is fundamentally a KT stress. So if I take a KT stress, I divide it by KT divided by KF, I end up with a KF stress. What that actually means is I end up with a stress from my final element analysis that is the stress that's basically responsible for the fatigue damage. So it's a way I can automatically go in and account for notch sensitivity in my material and in my part geometry and do a fatigue calculation. As a quick example of that, we have here a test specimen, a notch specimen that came out of the mill handbook guide. And this specimen gives me fatigue performance for this notch specimen. What we've done is taken that specimen and actually built it as a fine element model, so I can predict not only the peak stress at the bottom of the notch, but I can also calculate through DesignLife the stress gradient. We've actually done this for several different load levels. And then we calculate the fatigue life using the fatigue curves from the unnotched data. So coming out of the mill handbook, I had fatigue curves from an unnotched specimen. I also had fatigue performance of the notched specimen. And if I looked at the fatigue curve of the unnotched specimen, it's the red curve at the top. If I were to take that fatigue curve and use it with the stresses directly out of the FE calculation, I would predict a fatigue life that's the purple curve at the bottom. However, when we turn on the stress gradient correction, allow us to account for notch sensitivity, the actual prediction is the blue curve that you see. And overlaid on top of that blue curve are the test data from the notch specimen from Mill Handbook 5. The key here is we're able to go off and to correctly predict the fatigue performance, even though the material is not 100% notch sensitive. Finally, we're going to go on to the last aspect of today's presentation and looking at temperature effects. Here we're looking at the fatigue performance where we have an influence from temperature. And there's two major influences we could see. The first one we call high temperature fatigue, but here the thermal transients are really relatively long periods in time, but the actual stresses are caused by mechanical vibrations typically. And so we have some long thermal transient, but our stresses are generated from a relatively high frequency compared to the temperature transient loading. Here, the thermal transient and the mechanical vibrations aren't really coupled, and temperature here is, in essence, influencing our fatigue properties. It's not causing the stresses that will cause fatigue, but it is basically influencing the fatigue properties that will be used in the calculation. So what we need to do is be able to identify for a given cycle what the actual temperature was and use that in our calculation. And this would be indicative of things, examples here like this exhaust system, where the loading is primarily from the wheel base and the thermal influence is from the engine. And again, the temperatures aren't causing the stress, but they are influencing our fatigue properties. The other form of high temperature fatigue is one where the thermal transient is actually generating the stresses causing the fatigue. The example here is the exhaust manifold. On the exhaust system and the muffler, it was so loosely supported from the car body that when there was a temperature increase, it was allowed to expand and not really generate any stresses. The exhaust manifold, on the other hand, is rigidly bolted to the engine block, and so when it raises in temperature, it wants to expand thermally, and it's constrained from doing so. Hence, it generates thermal stresses. Two things happen. One, we have these large thermal stresses. Two, they're actually in phase with the temperature because the temperature is causing the thermal stresses. Three, we are sitting at that high stress condition, high temperature condition for a reasonably long period of time, and so we introduce creep as well. So basically two separate styles of problems, both we see in Powertrain. We're going to look at some of the enablers inside DesignLife to try to handle this. The first is the load provider. A load provider in DesignLife is a way that we take various finite element results and we're able to sequence them into a stress or strain temperature history that represents our part. And load providers we typically use will go in and do superposition point by point. And hence, we expect the histories all to have the same number of points in them, and we basically add them together. That's not the case with high temperature fatigue typically. We typically find in temperature-based fatigue that we have some loads of fairly long duration, things such as thermal transient. The temperatures themselves, and if the temperature change is generating stresses, the stress history as well will be a fairly long duration condition. If we have mechanical cycles with that, the mechanical cycles tend to be at a much higher frequency than the thermal. And here we're talking, we may have a thermal cycle of 20 minutes, but we have a mechanical cycle that's at 50 hertz. It's virtually impossible to go off in the FE analysis and to run a transient 20 minutes long and capture a 50 hertz signal. So we're looking for a way to be able to synthesize that inside DesignLife. And that's what the hybrid load provider does for us. It allows us to bring in a thermal transient at one time scale, hence 20 minutes, and bring in a snapshot of the mechanical vibration at 50 hertz, and basically be able to superimpose those and repeat the mechanical vibration such that we get the whole time history. It's a way to efficiently allow us to create these histories. So that's one of our enablers. Second, we need to have some way to characterize fatigue performance versus temperature. And so inside DesignLife, we have a variety of fatigue models: strain life, standard stress life, and a new one added at version 8, which is Shabash, which is an SN technique as well, that are fatigue curves versus temperature. In addition to those temperature-dependent fatigue curves, there's been an enhancement to how we count cycles. And the rainflow count for the cycles, now as it identifies the cycle pair as being a peak and a valley, it also is able to calculate the start and the end of that cycle. When did the cycle start in time and when did it end? And with that, we're able to go off and identify the temperature history for each cycle. So besides having temperature-dependent fatigue properties, we have now the ability to go off on a cycle-by-cycle basis and be able to identify the temperature history within that cycle. This allows us to go off, as we're doing the damage calculation, look at the temperature history for a particular cycle and pick its max or its average and use that as a temperature compensation for that cycle. Now obviously this works very well when we have high temperature fatigue, and what we have is like high frequency mechanical cycles being seen over a long duration, slowly changing thermal. It's not all that effective when we only have one major cycle, and that is the thermal cycle, and it's got the same duration as the time history of the temperature transient. So there's another approach as well. That approach goes in and uses the Shabash fatigue curves that we saw earlier, again, the family of curves at different temperatures. But now in this particular model, it uses a normalizing function. It goes off and tries to find some function of temperature that, if it applied to these fatigue curves, would cause these curves to collapse into a single curve. So we go off and we calculate some function of temperature that will take our family of curves and create a single curve from it. Once we have that function of temperature, we now can go in and apply that function onto our stress history. So if we look at the stresses coming out of the hybrid load provider, we have a temperature history and we have a stress history along with that. We take that normalizing function and apply it to the stress history, and now we correct that stress history point by point to compensate for temperature. Once we have that stress history compensated for temperature, we have the Shabash single curve, again compensated for temperature, and we use the two together to do the fatigue calculation. Finally, when we have these long duration thermal stresses, we typically will see creep. Fatigue is caused by changes in stress. However, creep is caused by just a constant stress. And if we have a stress state at a temperature over time, we run the risk of seeing creep. Besides having this additional strain, eventually creep can cause rupture, failure. And so what's built into DesignLife are creep rupture calculations that will look at the time at temperature and stress and calculate the percent to rupture we're at. There's two models built into DesignLife currently, a Larson-Miller as well as Shabash. And both of these will use the same time temperature profile of stresses that the fatigue used, but calculate creep rupture damage. And inside DesignLife, we have the facility to go off and run both of these together. So what we're looking at is a DesignLife model where we have a temperature stress history coming in from this exhaust manifold. Inside the solver in the center, we actually have, and we're looking at the advanced properties for that solver. You'll see that there's actually two analysis runs being run. The first analysis run is doing the temperature-based fatigue. So we're looking at the time, temperature, stress profile, and calculating fatigue damage from that. There's a second run that follows this, and this is actually running the Larson-Miller creep rupture calculation, using exactly the same time profile, but calculating the amount of damage caused due to creep rupture. And then DesignLife sums those two, does that Robinson rule, it sums those two, and presents it as results. So, in summary, what I've tried to do today is describe some capabilities inside of nCode DesignLife that enables you to look at various powertrain applications. We start off looking at a new stress-based factor of safety calculation that's available in 9.1. We also went back and revisited the standard life-based factor of safety that we already had in DesignLife, and that's actually applicable for both high cycle and low cycle fatigue. We looked at using DesignLife for what we call vibration fatigue, but what that is really is using DesignLife as a virtual electro-dynamic shaker table that allows us to do random loading to do our fatigue predictions. We looked at how DesignLife uses stress gradients to do an automatic compensation for notch sensitivity. And again, this is very, very important as we start looking at cast metals. Many cast metals are very, very notch insensitive, and ignoring that can give you basically nonsensical results. And then finally, we looked at the availability of having temperature-dependent fatigue models and creep models inside of DesignLife, along with the hybrid load provider and the enhanced rainflow counting to allow us to go off and do both high temperature fatigue calculations as well as full TMF, thermo-mechanical fatigue problems. And with that, I think we'll bring this back to Amanda, let her bring up the survey, and then I'll take questions.